All right, 7.1.5 is how can I eliminate the fractions? So we've been talking about coefficients, and it's very important to know that term. And it says creating integer coefficients. So if we think about what a coefficient is, a review of yesterday, a coefficient is, say you have 5x plus 2 as your expression, this 5 would be the coefficient because it's the number that's attached to the variable. So that is what a coefficient is. Now it's saying we're going to be creating integer coefficients. So remember, an integer is negative whole number, negative and positive whole numbers and 0. So no fractions. Integers are not fractions or decimals or percents. So whole numbers. Integers are whole numbers. So we want to, in the intro, it's talking about one of the best ways to deal with a challenging task or problem is to find a way to make it easier. And I know we all like to make our problems easier and find little shortcuts and that type of stuff. So that's what we're going to be doing in this lesson, is really challenging problems with fraction coefficients can be made easier. And that's what the gist is. Making stuff easier on ourselves, which is important so we don't get too frustrated. So our first problem is going to be 751. It's called community service. So it says the Community Service Club at North Middle School is planning to paint apartments at the local senior citizen center next week. The club needs your help to determine how many apartments they should be able to paint in a day. Earlier in the year, when only 4/7 of the students worked, they painted 9 apartments in one day. Next week, all of the students are available. So let's see what part A says. Assume that all of the student workers contribute equally to the work. So each kid contributes the same amount of work as the next kid. If X represents the number of apartments, that can be painted by all of the students in the club, use a multiplier and your understanding of scaling to represent this situation as an equation. So an equation is going to have something on one side of an equal sign and the other side has stuff on the other side. So we need to make an equation. So I need an equal sign to start. We know that X is going to be our variable for the number of apartments. And we know earlier, so the stuff we already know is that earlier in the year, when there was only 4/7 of the entire students, the total number of students available, they painted 9 apartments in one day. So what I'm going to do is I'm thinking to myself, well, I'm going to take that fraction 4/7 and I'm going to multiply it by the amount of apartments, and that's going to equal 9 apartments. So, right, it says X is number of apartments. So if 4/7 paints 9, we're going to figure out how many all of them can. So pretty much this is saying 4/7 is 4/7 of what number is 9. So let's figure out says to choose a strategy to solve your equation in part A. So now we're at part B. What does your answer represent? So we have those strategies we had to get rid of the fraction in the last lesson. So we can have, there's one of 2 ways we can do this. We can multiply the equation by 7/4 to make a giant 1. Or you can divide the whole equation by 4/7 to make a giant 1. I'm going to do the multiplying one because that's easier on my brain, because I don't like to see 2 fractions stacked on top of another. I don't like it. Doesn't work well with me. So 4/7 x equals 9. So let's solve this. I'm going to multiply this side by 7/4. So that's going to make a giant 1, and I want that x all by itself without any number attached to it. Then I have to do the same thing to both sides because we have to balance. We have to balance the sides. Okay, so this is going to be our giant 1, which just becomes an x down here. Then we're going to multiply across. So 9 over 1 times 4 over 7 is, whoa, that should not be 4 over 7, that is 7 over 4, because we did it here, that was my mistake. Okay, so 9 times 7 is 63, 63 divided by 4 is 15.75 apartments. So that is the amount of apartments if the entire total of students were there. That's how many apartments they could paint. If there's only 4/7 of the kids there, then they can paint 9. So we kind of want everybody there because then we paint more apartments. Okay. 752. This is going to be another way to solve these types of problems, and it's going to use the equation map. So it says Janice, the club's president, began to think about how she could visualize 4/7 x to help her solve the equation from the last problem. So she remembered the algebra tiles, and she visualized this diagram, and I'll draw it, even though it's in your book. And it has a dotted line, and then it has an equal sign, and then it has this bar that's divided into 7ths, 1, 2, 3, 4, 5, 6, 7. And then it has 4 of them shaded in, so 1, 2, 3, 4. And then it has the little bracket thing to show us that all of it is x. And then it has 9 cubes, and I'm arranging them a little differently. And they're all filled in. We're just using positive numbers right now. Okay, so now it says part A. Does this equation map represent our equation from problem 751? Why or why not? So I'm looking at it, and I'm noticing 4/7 of this x equals 9. And that makes sense because what we wrote in the last problem was 4/7 times x equals 9. So she is correct in her diagram, because all 4/7 means is 4/7 of whatever x is equals 9, and that of means multiply. Okay, B says Janice recognized these numbers were not easy to work with since she didn't have whole tiles with the fractions going on. So after working on her paper for a while, she said, maybe I can make whole tiles using more than one set of partial tiles. So she drew this diagram. I'm not going to draw that because there's a lot going on, but I'll just explain it because you can look at it in your book. So it looks like it says, what is her new equation as represented in this picture? So it looks like she's got 7 groups, right? 1, 2, 3, 4, 5, 6, 7. So she's got 7 of these total on that side, so times 7 of those on that side. And then she's got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. So she's got 63 little unit tiles on that side. So it says, what is her new equation? So her new equation, are we on 752? Yes. And we're on B. So her new equation, if I multiplied each side by 7, I'm having how many 7ths? Now it wants us to know how many 7ths are shaded in on this side. So I'm going to count all my shaded ones. So I see 1, 2, 3, 4, 2, 3, 4, 5, 6, 7. So 7 times 4, there's 28 sevenths. And that's times by x equals, and there's 63 little cubes, 63. So that would be her new equation, represented by that equation mat in your book. So now it says, work with your team to discuss her strategy for solving. We're going to answer the following questions for C. So it looks like there's 4 bullet points under C. So I'm going to rewrite this up here. 28 sevenths x equals 63, so we don't forget it. Okay, this is C, and this is the first bullet point. What made her strategy different than what you did in the last lesson? So her strategy focuses on whole x tiles. So I'm just going to put her strategy equals whole x tiles. So that means that you would have a whole number coefficient, because if you take 28 divided by 7, you get a whole number, 4. So you would be left with 4x equals 63. So it says, how many sets of 4 sevenths x did Janice use to get a whole number of algebra tiles? Well, we figured out that she used 7 sets of 4 sevenths to make a whole number. I know it's kind of hard to grasp. So we're going to say she used, that's why we're going to write it down. She used 7 sets of 4 sevenths to get a whole number. Okay, so then it says, why did the right-hand side of the equation change? So why did this 9 become 63? Not by magic. So what we set up here, she multiplied both, keyword both sides of the equation to make it balanced. And I'm not going to write that, but that's assumed that if you do something to one side of the equation, you have to balance it out on the other side. Last bullet point says, how does the number of sets Janice used relate to the equation you wrote in part A? So she used how many sets? She used 7 sets of 4 sevenths. So how does that relate to this 4? Where am I going to write it? I'm going to just erase this now. 4 sevenths x equals 63. So it is, there we go. So where do we see 7 in this equation? Well, it's right here. It's our denominator. So it's the fractions denominator that she multiplied the equation by to make it easier to solve with a whole number coefficient. Yep. So the last bullet point would be 7 is the denominator of our fraction, 4 sevenths. It's the same thing she used to multiply. Okay. 53. Okay, we've got 2 to go. This is just breaking down the steps and how to, and what it means to create an integer coefficient. Okay, part A. Will the strategy of turning fractions into integers from the last problem work with other equations, such as 2/3 x equals 8? Consider this question as we answer the following. So part A says, how many sets of 2/3 x would make a whole number of x tiles? So it says, well, we know that she used 7 sets for 4 sevenths. So what do we think that she's going to use for 2/3? third set, she's going to use 3 because 3 is our denominator. So she's going to use 3 sets of 2/3. And then it says for part B to solve it the way that Janice did. So we're going to draw it. There's our equation map. So now I'm going to draw it the way she did, but with this problem. So I'm going to draw 3 sets of 2/3 and shade in 2/3. Okay, so now on the other side, if we have 3 sets of 2/3, we need to make 3 sets of 8 because we have to balance the equation. So 3 sets of 8, 1, 2, 3, 4, 5, 6, 7, 8. And for sake of time, I'm just going to put times 3, which is 24 units. So there'd be 24 cubes on that side. So now it says, oh, it wants us to solve for x. So if we have 3 sets of 2/3, we know that 3/1 times 2/3 gives us 2. So we're left with 2x equals 24. So if we solve for x, 2 times what gives us 24? 12. And I showed the extra step of dividing both sides by 2 because we want to get that x alone. So x would equal 12. Part C says, show how your solution is also the number of 2/3 in 8 wholes. 8 divided by 2/3. So 8 divided by 2/3 means how many 2/3 are inside of 8. So if we solved that, it would look like this. 8 times 3/2, which means 24 divided by 2, which is the same as saying 12. Okay. Last one. That was 753. Here's 754. Janice wondered if the method of creating whole number x terms would work with decimals. Suppose an item was marked 15% off and the sale cost was $36.21. So the item is 15% off and the sale price is $36.21. So here's the equation that you see in your book. 0.85x equals 36.21. So A says, why did she write 0.85 in her equation? Well, I'm noticing that 85 plus 15 is 100%. So if 15% off whatever the total was, that means that 85% is what she's paying for. So 85% of the total price equals the sale price. So I'm going to put, I'm going to write it here. 85% represents the price paid after the discount of 15%. So if you calculate 0.85 times the total, that means you'll get the sale price. So here's the sale price. This is going to be the total price, and 85% is that. Okay. Is there a number for part B that she can multiply both sides of the equation by to get an integer coefficient, so there's no decimal? If so, list at least one. If not, explain why not. So I rewrote the equation down here. And what she can do is, well, if I wrote this as a fraction, 85 hundredths x, okay, because that is the same thing as that, could I multiply both sides by a number to get a whole number on this side. So there's an option that I thought of. If I want to get rid of that 100 on the bottom, what did we do for the 2/3 in the last problem and the 4/7 in the even laster problem? That doesn't make any sense, but you know what I mean. I'm going to multiply each side by 100, because if I do that, that's going to cancel out that 100 and make it a whole number. Then I'm going to multiply that side by 100 to balance it out. So now I bring down that 85x, because that's all that's left. And then 36.21 times 100, don't even have to bring out a calculator. Just move the decimal over to the right twice, because you're multiplying by 100. And now it's a lot easier to solve with these whole numbers, because now to get x by itself, and I think I'm moving on, yep, here's C, we are going to solve the equation. So to solve the equation, we want to get x alone. So divide both sides by 85. Plug that into your calculator. That becomes a giant 1. So the x is the only thing left on that side. I plugged this into my calculator and got $42.60. Now for part D. Does this method work for all equations with decimal coefficients? And I'm going to say yes, it does. The strategy will work for any decimal, because when you write a decimal, it's really just a portion of 100 or 1,000 or 10,000 or 10. So you can easily rewrite a decimal as a fraction and then eliminate the denominator by multiplying the denominator by both sides of an equation. So let's kind of sort that out. So I'm going to put the strategy works. Strategy works, but then it's asking, what if you wanted to solve the equation 1.2x equals 14? What about 0.999x equals 71.2? So we could do that with these. So what I'm looking at for the decimal, it's kind of interesting, because if you look at the decimal you're working with, you're just going to ask yourself, well, how many tens do I need to multiply this by to move the decimal so that it's a whole number instead of a decimal? Well, I notice if I move this decimal over to the right once, I get the whole number 12. So if I do that on that side, I need to do that on the other side as well. So that would be 140, and that would be 12x equals 140. So that means I pretty much multiplied both sides by 10. This one's going to be a little different, because how many places do I need to go? 1, 2, 3 to make it a whole number with no decimal. So that would be 999x equals, and then same thing, 1, 2, 3, 71,200, which means I did not multiply by 10. I didn't even multiply by 100. I multiplied by 1,000 that time. Okay, so you got to keep in mind how many tens you're using to multiply the decimal in order to make it a whole number. And that is the end of this lesson, and it's very hot in here.